Okay, everyone. Good morning or afternoon, whatever time you're looking at the video. We're going to start our 1 week general review. We're just going to generally review the topics. You will be receiving home in the next couple of days a couple of packets in a folder. One is packet one is packet two. One of um, the actual AP tests. The other one's a practice AP test that they gave out. Um, and we'll be reviewing those once we finish the general review. So I'm just going to get started, get into this. I'm going to try to record for about 20, 22 minutes. You'll watch out, give you some questions to do in the AP book, and we'll go on from there. Okay, so we're going to be talking. Oh, I don't know, I have a stylus, so I need a stylus for this. We're going to be talking about limits. A limit is just a value you approach. As you get closer and closer to a certain x value, you're going to get closer and closer to a certain y value. There are generally three types of limits we're going to look at. Those are limits that we approach from the left side. And we'll put a check here because we're going to go over that. A limits we approach from the right side. And if there's no number up there, it's the number we approach as we come from both directions. The only way to have a limit in both directions is for both sides to head to the same location. Okay? And sometimes that happens, and sometimes that doesn't. One of the most common functions the AP will look at, more on multiple choice, but it's still good to know about right now, is what's called the int function. And the int function looks kind of like this. Sometimes I'll write it like this, and sometimes I'll write it like that. And all the int function does is it takes whatever number you have, and instead think of it like the game with the hammer at the what do you call it? At the carnival, where you got to slap the hammer down and the weight goes up. It goes up as high as it goes. Well, we're going to think of it that way. Let's say you have a decimal 6.6. You're going to always go backwards to the nearest whole number. Meaning, if I get up to 6.6, the value, it's instead of rounding, it's basically dumping the decimal and going back to the nearest whole number. So this would end up being just 6. It makes sense for whole numbers. For example, if the int value is 3.9, if I'm at 3.9, I'm going to come back down to the nearest whole number. It's going to go down to 3. And then if I'm at 0.3, I'm never going up. I'm always going down to the nearest whole number. The nearest whole number would be 0. And then the only time it can be a little tricky is when we're dealing with negative numbers. So watch, if I just draw a little number line here. And feel free to add these notes on in. Negative 2.9 is like right here. Negative 2.9 is in there. We're never going to go up. We're never going to go in that direction. So the int value of negative 2.9 is always to go backwards to the nearest whole number. So it's going to go to negative 3. So remember, we're always going backwards. Now, values are different necessarily from the limits. So for example, what is the limit as x approaches 6 from the negative direction? Oh, and this is the graph of that function. What is the value as x approaches 6 from the negative direction of x? Well, if I go to the x value 6 and look at what value I'm approaching as I come from this direction, the value I'm approaching is going to be 5. So the next one says, what's the value as I approach 6 from the positive direction? If I come from this direction, what value do I approach? I approach 6. And that makes sense. If you look at the picture here, I'm heading to two different locations. I'm heading to this value as I approach 6 from the left side versus this as I approach from the y side. This is actually called a step function, which we talked about. And the limit of this function as x approaches 6 does not exist. The limit does not exist because I do not approach the same exact value. Now, a lot of times on the AP, instead of us doing numbers, we're going to get to that. They're going to give us pictures or they'll give us shapes and ask us about the function as time goes by. I think I got this camera set right so I can just adjust things. There we go. Please remember there's a difference between finding a value and finding a limit. Sometimes one exists and sometimes the other one does not. So now let's look at functions graphically and numerically. We're going to look at limits of the function 1 over x. Or the 1 could be any constant. It doesn't matter what it is. All those graphs are going to look much like this graph does right here. As a matter of fact, there's a vertical asymptote. I will highlight it in red. Let's pick a good color. Aqua. This one is a vertical asymptote. The graph approaches but never touches that one. There's also a horizontal asymptote. which the graph approaches but never touches. And we can look at things as we head off towards different numbers. So let's see if these answers make sense. Let's look at the limit of f of x as x approaches 0 from the positive direction. So as x gets close to 0 in this direction, what y value am I approaching? Well, it's going up and up forever. So the limit as x approaches 0 from the positive value is infinity. Now let's look at 0 from the negative direction. As we approach the x value of 0, I'm going to stay on the curve, the x value of 0. The graph is going down forever. The limit is negative infinity. The negative sign just denotes direction. And why does the limit as x approaches 0 does not exist? Because it does not approach the same value in both directions. If both of these said infinity, it's a different story, but they don't. They're heading to different locations. So these were limits as we approach the number that headed towards infinity. Now let's look at limits where we head for infinity. So this is as x approaches infinity. Notice there's no plus or minus sign in here. When you're heading towards infinity, there is no other side to infinity. So it's always just what's going on as we head in one direction. So as we head towards positive infinity, this graph heads towards the x-axis. So the height of the graph heads towards 0. As we head towards negative infinity, the height of the graph heads towards the x-axis. So the height of that graph heads towards 0. The other big thing to remember on these is that this side of the graph is always x values, and this side of the graph is always y values. So you can think of it that way. When x is 0, y is infinity. When x is 0, y is obviously up towards infinity. Okay, now let's take a look at some piecewise functions, which are made up of different parts. This first column is asking me for values, f of whatever. So let's see if I can find those. F of negative 2 does not exist. There is no value there. There's a hole, but there's no value. F of 0 is going to be 3. F of 2 is going to be where the filled in dot is, also 3. Oh, f of 1, who said 2? F of 1 has no value. There's no dot there. F of 2, the dot is at 3. And f of 4, the dot is at negative 2. So those are telling me actually what the value was there. The limit is going to be as we approach. As we approach negative 2 from the left and the right, the height of the graph appears to be at 1. So once again, I'm heading towards that height of 1, even though there's no actual value. And the limit as x approaches 0. Once you have this nice, smooth, continuous function, you don't even have to try. If the function is smooth and continuous there, the limit and the value will always be the same. As a matter of fact, that's the definition of continuous. Definition of continuous is the limit from the left equals the limit from the right equals the actual value. We'll see that coming up in time. Let's take a look. The limit is x approaches 1 of f of x. So let's go to 1. And if we see, it goes up on one side forever, up on the other side forever. So there are two correct answers here. One is D and E, because the limit does not exist. But you could also say that the limit is infinite, because it's always heading up. It's different from the problem before, where the arms were heading in the opposite directions. Both answers would be correct. I assume because ours is going to be a calculator-based question, you could put down either, but sometimes they're multiple choice, or they might give us a choice. I don't know how they're going to work it, and you might only be able to choose infinity as your answer. So let's look at the limit as x approaches 2. As x approaches 2 from the left side, it approaches a different spot than x approaches 2 from the right side. Therefore, the limit does not exist. And as x approaches 4, once a graph is smooth and continuous in an area, don't even try to figure it out. It's the same as the value. It's negative 2. Okay, so there's our general info on limits involving graphs. Next thing we're going to do, we're going to finish our limits thing. We got about 10 minutes or so to go. There we go. Limits continued. So these are just some general guidelines to problems. I'm actually going to show this page and then break it down to a little bit easier version of it so that you don't have to remember as much. Okay, first of all, on the last page we saw there were asymptotes. Sometimes those asymptotes are vertical, and vertical asymptotes occur whenever the bottom of the function is undefined. So for example, this particular function, we could graph it, would have vertical asymptotes, x equals negative 2 and x equals negative 3, because that would make the bottom of the graph 0. And we have horizontal asymptotes is when we head off to infinity and our graph approaches a number. The only time that's going to happen, we're going to explain more about this with L'Hopital later on. And there's nothing specific I remember here. It's just giving you a general idea of things. The only time that you'll get a horizontal asymptote when you head to infinity is if the degree of the function matches on top and bottom. As a matter of fact, for this particular function right here, they would have a horizontal asymptote at x equals 4/9. Here's the reason why. As I head to infinity, the only thing that matters is the biggest exponent. The other exponents are so small compared to it that they legitimately don't make a difference in the size of the number. So this is not real math, but this is kind of like limit math. I could say the only thing that matters is the biggest exponents, which are squared. All of these things are totally unimportant. I can just throw them away. It's like x squared being worth 100 trillion and x being worth $1. They're just unimportant. So remember, that's just limit math. I just deleted those things. How can I simplify this after that? I can cancel those out and I'll get 4/9. We're going to use L'Hopital's rule to do this specifically. And with your calculator, it's pretty straightforward on how to do it. So I'll come back to what I just went over right here. But for right now, know that if you head towards infinity, the only time you have a limit is when the exponents match each other up. Okay. In the past, they wanted you to use on the AP something called a special case problem, which is called the squeeze rule. And the squeeze rule allowed us to prove that certain functions reach certain things. For example, I know if I graph this, the limit as x approaches 0 of sine x over x is equal to 1. And the reason I know that, is, A, if I graph it, I could see that case. In the past, we would use a squeeze rule, which you actually saw on the notes from the other day. And the squeeze rule just said if you have one function, actually if I graph one function and graph another function, and the other function is always between them, then they have the same limit. We're not going to worry about that right now. We may just see that word. What we're always going to use is L'Hopital's rule to solve limits, and I'll just show you what that means. If I were to take this original problem, this is a preview of L'Hopital. I'll go into it more in a minute. Which is 0 of sine of x over x. If you put 0, you always take your 0, your value, put it into your function. Sine of 0 is 0. Put in 0 for x, 0 is 0. I get indeterminate. It means I don't know what the limit is. If I put a number in and got a number, I've got the limit out. L'Hopital's rule says if you got this indeterminate form, you can do the same thing again. Infinity to 0. But take the derivative of the top, which is cosine of x. Take the derivative of the bottom, which is 1, and substitute it in, and the limits are exactly the same. So the limit of that is 1. Once again, this is just a preview of L'Hopital. L'Hopital says if you get this form, just take the derivative of the top and derivative of the bottom, and the limits will be the same. We'll get into that more as we move on in the pages here. Okay, the next thing is the rational function theorem. I don't like these words, rational function theorem. Rational just means ratio. Function theorem, if we look at the pictures we have right here, we can see they're all fractions. This only works for polynomials, and it's just a shortcut for L'Hopital. If you don't like this rule and you want to block it out, feel free in a few minutes. Basically, when you're heading to infinity, only the biggest exponent matters. That's all that matters. Let me show you what I mean. From heading to infinity, and I put I'm going to head towards infinity, only the biggest exponents matters, I can throw all these away. I can just chuck them, because they don't make a difference. I can cancel these, and I get a limit of 25 over 5, which is 5. Let's take a look at the next one. The next one, as we head toward infinity, the biggest exponent is x to the 5th. Well, there's none of that on the, I'll get rid of everything else on the bottom. And on the top, because there's no 5th there, it's just like having a constant on there. Okay? And then we have to think the limit is 1 over infinity, or 1 over some really large number. And 1 over a really large number, if you think about it, like 1 over 1 million, 1 trillion, is close to what number? 1 over that number is close to 0. That's our answer right there. And there's another example as we head towards infinity, where only the biggest exponent matters. This is like having a number. Down there is 2. So infinity over some number is going to be infinity. So kind of like what I talked about way up on top. If the exponents match, then it has a limit. If the bigger exponent's on bottom, it heads towards 0. The bigger exponents on top, the limit heads towards infinity. We don't really use it as much with these problems over here. Excuse me. If we go ahead and substitute in 0 in for all these, this becomes 0. Those go away, and we're